So following the discovery of the atomic nucleus, we have this picture of the atom emerging. You have the atom itself with the electron cloud. You have the nucleus, which contains both the protons and the neutrons. Protons positively charged, neutrons with no charge. And then you have the electrons surrounding the nucleus in what has become known as the electron cloud. And we'll have a lot more to say about that when we get to quantum mechanics. But in general, that's our description at this particular point in time. Now, atoms are neutral species. Now, protons have positive charges, and they're located down here in the nucleus. So however many protons you have in the nucleus, if you were talking about an atom, you have to have the same number of electrons surrounding the nucleus. That's because atoms are neutral. So the number of protons has to equal the number of electrons. Electrons are electrically negative. They have a negative charge. Protons are electrically positive, and since atoms are neutral, these two numbers have to match, the number of electrons and the number of protons. Let's take a quick look at this periodic table and the way that it's organized. It's a magnificent scientific accomplishment, first described by a gentleman known as Dmitri Mendeleev, who originated in Siberia and ultimately made his way to St. Petersburg in Russia, where he became a prolific scientist and one of the greatest minds of his time. And he came up with the first periodic table. So the periodic table starts out with hydrogen up here on the left, and it is atomic number 1, meaning it has 1 proton in the nucleus. And then we have helium, which is atomic number 2. It has 2 protons in the nucleus. Lithium, 3 protons. Beryllium, 4. Boron, 5. Carbon, 6. Nitrogen, 7. Oxygen, 8. Fluorine, 9. And neon, 10. And so on. And for atoms, just remember the number of electrons has to equal the number of protons. We call the number of protons that are in the nucleus, we call that the atomic number. And that's how we identify elements. So if we've got carbon, which is atomic number 6, that number of protons, 6 protons in the atomic number, that's how we identify it as carbon. If you change that to atomic number 7, you no longer have carbon, you have nitrogen, and so on. Determining the number of subatomic particles in an atom. Here we go. This is easy. The atomic number is equal to the number of protons. So just look at your periodic table. That will tell you what the atomic number is usually, and you can from that determine the number of protons. And if it's an atom of that particular element, then it's also the number of electrons, because the number of protons equals the number of electrons as long as what we're talking about is an atom. The number of neutrons, a little bit more challenging. Every isotope, what we call isotope, has a specific number of protons and a specific number of neutrons. And when you add those two together, the number of protons plus the number of neutrons, that equals the mass number. So all you have to do to get the number of neutrons is take that mass number, subtract the atomic number, which is the number of protons, and that's going to give you the number of neutrons. It's a piece of cake. So here is our periodic table. We can quickly look at iron and see that it has 26 protons in the nucleus because its atomic number is 26. That whole number on the periodic table is going to be the atomic number for that particular element. Zinc has 30 protons in the nucleus because its atomic number is 30. Sulfur has 16 protons in the nucleus, and chlorine 17. Bromine 35. Cobalt 27 protons in the nucleus. And osmium has 76 protons in the nucleus, and so on and so on. Okay? These are the weighted averages of the atomic masses. These are not the mass number. Mass numbers are whole numbers. Remember that. All right, so first thing we need to do is figure out how we write different isotopes of elements. And isotopes differ by the number of neutrons and therefore the mass. This is the mass number for a particular isotope of an element. Now, what's not indicated here is the atomic number, but typically it will be. So here is the atomic number. Now, you automatically know that if you see, this is cobalt, and if you don't see the atomic number down there, just go back, look at your periodic table. There's cobalt. Its atomic number is 27. That tells you it has 27 protons, which I'll just indicate as +1. There's no charge indicated up here on the as a superscript on the upper right, so you know it's an atom, and so that it's also going to have 27 electrons. To get the number of neutrons, we simply subtract the number of protons from the mass number, which is a whole number, and that gives us 32 neutrons. I'll go ahead and spell that out. Okay, so we have 27 protons, 27 electrons, 32 neutrons. Okay, and that is how you find the number of protons, electrons, and neutrons in a particular species. All right. Ions. Ions are charged particles, and charge just means it's either positive or it's negative. That's all it means. It has a charge, and there's only two flavors, plus or minus. Now, you could have +1, +2, +3, or -1, -2, -3, and so on. We've got specific names for the charged particles. So if our charged particle is called a cation, that means it has a positive charge to it, and that means it has more protons than it does electrons. Because if you remember, what we've got here is we've got a number of protons, and it's equal to the number of electrons if what we're talking about is an atom. However, if a species gives up electrons or accepts electrons, it's going to have a different number of protons and electrons, a surplus of one charge or another. We use the word cation to describe ions that have more protons than electrons. Now, you can't change the number of protons for a particular element. If you change the number of protons, you change the element. So it's all about whether electrons leave or are acquired by a species. Now, in the case of a cation, electrons leave. So for instance, if I have calcium metal has atomic number 20. That means it has 20 protons in the nucleus. Calcium as a metal has a propensity to give up electrons, not to accept electrons. So calcium tends to become a cation, a positively charged ion, and it tends to give up 2 electrons when it gives up electrons. And so this would be a calcium 2 plus cation. It's a cation because it still has 20 protons in the nucleus. You can't change that without changing the element, but since it's given up 2 electrons, there are only 18 electrons remaining. It just has a +2 charge. It is a cation because it's given up 2 electrons. Anions, on the other hand, have a negative charge to them. They have more electrons than protons. So let's pick chlorine. So here's chlorine, And chlorine has a propensity to accept one electron. Now, chlorine has an atomic number 17. It has 17 protons. You can't change the number of protons, or you change the element. But if it accepts an electron, then it becomes a chloride anion. It still has 17 protons in the nucleus because it's still chlorine, but it's got an extra electron, so it has 18 electrons. So anions are negatively charged species, and so the chloride ion would be an anion. Now I'm going to scroll back to the periodic table that we were looking at, and I'm going to make some distinctions for you. If I draw a line, you can see the shade that goes down this side of the table, and I'll draw it on the other side as well. We're going to go into this in a little bit more detail, but just for the sake of forming ions, I'm going to emphasize something, all right? Everything on this side of this line, okay, aluminum, gallium, tin, bismuth, polonium, all these guys over here and these guys down here, these are all what we call metals. And metals love to lose electrons. We'll find out later why when we get to the properties like ionization energy, but at this point in time, all you need to remember is that metals tend to lose electrons. Well, that means that metals, since they love to lose electrons, they tend to become cations. And cations are positively charged ions. So let's take iron, for instance. So here's iron, and you're familiar with iron. Iron has 26 protons in the nucleus because that's its atomic number. It also has 26 electrons as an atom of iron. But iron, like all metals, has a tendency to give up electrons, and let's say it gives up 3 electrons. So 3 electrons go bye-bye. Now we have a 3+ cation. It still has 26 protons in the nucleus because it's still iron, but it's lost 3 electrons, so it only has 23 electrons remaining because 3 electrons went bye-bye. All right, on the other hand, oxygen. Take a look at oxygen. Oxygen is what we call a non-metal. Everything to the right of this line is what we call a non-metal. And with the exception of the noble gases, they don't like to react. That's why we call them noble. These guys over here, they like to accept electrons and become anions. Okay, so let's take oxygen. Oxygen typically would like to collect 2 extra electrons to become an oxide anion. Now, oxygen still has 8 protons here. It has 8 protons here because it's oxygen. But now, oxygen, instead of having 8 electrons as an atom of oxygen, it now has 2 extra electrons, so it has 10 electrons as an oxide anion. Now, these elements that are in here, these are called the metalloids. We'll talk a little bit more about them a little bit later, but they have properties of both the metals and the nonmetals. All I wanted to reference here are ions, and positively charged ions have more have more protons than electrons. We call those cations. They are positively charged. And then anions, these guys over here tend to form anions. They accept electrons, and they have more electrons than they do protons. Okay, all right, so here is the way we typically designate with this kind of representation an ion. We'll put the charge up here. Now this is indicating that this is a cobalt cation. Now if I look at my periodic table, I see that it's still cobalt. It has an atomic number 27. It has 27 protons. So there's 27 protons, but it's a cation. It has a positive charge. Electrons have a negative charge. So if two negative charges have left, you have two more protons than you do electrons, so that leaves you with 25 electrons. Remember, electrons are negatively charged, so if something has a positive charge, it means it's lost negative charge. It's still cobalt 59. We haven't changed the isotope, so it's still going to be 59 minus 27, which gives you 32 neutrons. And so 32 neutrons. So in this case, we've got 27 protons, 25 electrons, 32 neutrons, and E would be our answer. Complete atomic symbols. We've got the mass number, so you just take the symbol, whatever it happens to be. This could be calcium, potassium, it could be chlorine, it could be boron, doesn't matter. The mass number, which is the sum of the protons and the neutrons, gives a superscript to the upper left, just like you've seen. The atomic number typically will go as a subscript to the lower left. If there's a charge, you put it up here as a superscript to the upper right. So, for example, this is boron 11. It could also be written as boron dash 11. That's the way you would write that isotope. It's got an atomic number of 5. That means it has 5 protons. There's no charge up here, which means it has 5 electrons, and then 11 minus 5 is 6 neutrons. And that's the way you analyze that particular symbol. Isotopes, which I have talked about a little bit, atoms of an element which vary in the number of neutrons, therefore the mass. If you go back to the lecture on John Dalton's 4 postulates, depending on how you write them, 4 or 5 postulates, but the second postulate describes atoms of a particular element having the same properties, including mass, and that we determined was incorrect, and I said that's because isotopes have different number of neutrons. Now, neutrons and protons in the nucleus, they're what we use to determine the mass number of a particular element, not the electrons, which contribute very little to the actual mass of the atom. And so Dalton was wrong about that, but he had no way of knowing about isotopes. Carbon seemed like carbon, whether it was carbon 12 or carbon 13 or carbon 14. There was no way for him to tell in his day, so he did a pretty good job. But if you have a different number of neutrons, you have a different isotope of a particular element. For example, here are 3 different isotopes of hydrogen. Now, this is called protium. It is the most abundant isotope of hydrogen in the universe. It has 1 proton in the nucleus. 1 minus 1 means it has 0 neutrons. And it's an atom, so it has 1 electron. So 1 proton, 1 electron, 0 neutron. This is deuterium. It's heavy hydrogen. And it still has atomic number 1, so it's still hydrogen, so it has 1 proton, but it has 2 minus 1, which gives you 1 neutron, and it also has just 1 electron because it's neutral. There's no charge indicated up here. So this is heavy hydrogen, actually has a neutron in the nucleus. This is tritium. It's 3 minus 1, 2 neutrons in the nucleus. It's associated with radioactivity, nuclear reactions, actually. And it still has 1 proton, 1 electron, but it has 2 neutrons. So these different isotopes differ in mass because they differ in the number of neutrons that are in the nucleus. Atomic mass. So we talked about measuring the mass in grams, and we had really small values in grams for for protons, neutrons, we're talking about 10 to the minus 24 for protons and neutrons, and 10 to the minus 28 for electrons. So we need a new unit of mass for these incredibly small species. And so what we're going to do is we need a standard. So for instance, if I'm going to measure a particular length in meters, there is a defined length of meters. It used to be a platinum rod kept in a vacuum vault in Paris. Now it's simply the distance light travels in a vacuum for a very, very tiny bit of time. That's the official meter. But for the elements, we use carbon-12. Now, carbon-12 is very stable stuff. We would write it like this. So here I would write carbon. It has 6 protons. It's the isotope carbon-12. 12 minus 6 is 6. So there are 6 protons in the nucleus, and there are 12 minus 6 neutrons in the nucleus. 6 plus 6 is 12. We take 1/12 the mass of an actual single carbon-12 atom, and that becomes our conversion factor. And the units that we compute with that give us the relative mass in what we call atomic mass units, or AMU. Anytime you're talking about AMU, you're talking about particles on the atomic molecular level. So you're really talking about the smallest components when you're talking about AMU. So here we go. The mass of a hydrogen atom in grams is 1.635 times 10 to the minus 24 grams. The mass of a carbon-12 atom is 1.9927 times 10 to the minus 23 grams. What we're going to do is we're going to take that mass of a hydrogen atom, and we're going to use 1/12 the mass of an actual carbon-12 atom, and when we do this division, or we multiply the numerator by 12, divide by the actual mass of a carbon-12 atom, we come up with 1.0078, and the units are AMU. Okay? All right, I want to introduce you to a really great periodic table. Here it is. It's dynamic, and it's in your PowerPoint notes. It's also, there's a link on Canvas for it. So if I want to know something about nickel, all I have to do is hover over it, click on it, and it's going to bring me the Wikipedia page for nickel. It'll show you what it looks like. It's a shiny metal, lustrous, metallic, silver. It's going to give you some of those characteristics. It'll give you the standard atomic weight in AMU. It's also going to give you a thing we call the electron configuration. When we get to quantum mechanics, we'll talk about that. And different properties, its density, heat of melting. Fusion is called melting. Fusion is a more technical term. Its boiling point, the heat of vaporization, etc. So in any case, lots and lots of information. So any element that you want to know something about, if you simply get that periodic table up, roll over an element, and you can find out an awful lot about those elements. All right, so let's go back. So average atomic mass is based on the number of isotopes for a particular element. It's dependent on the relative abundance, and the relative abundance it's just a different way of saying the percent abundance of that isotope. And it's dependent on the atomic mass of each one of those isotopes. And here's the equation that we use to determine the weighted average. And that weighted average, based on the number of isotopes and their percent abundance, is called the average atomic mass. And it is what we call a weighted average. And let me show you how we do that. We take the sum of the mass of each individual isotope times its percent abundance, and then we add them all together. That's what this means. This is the sum of. So let me show you how to do that. Once you know how to do it, it'll be a piece of cake. So here's our example. The element X has 3 naturally occurring isotopes. The masses in AMU and the percent abundances of the isotopes are given in the table below. And essentially this is just asking me for what is the average atomic mass in atomic mass units, AMU. So we see we have 3 isotopes for element X, isotope 221, 220, and 218. Now, let me give you a clue. This is the percent abundance, and we see that most of this element atomic mass comes from isotope 221, which has an actual mass of 220.9. So what that means is, unless we have something that has a really low atomic mass for a particular isotope, we should get a weighted average that's closer to this. Now, I do see that isotope 218 is considerably lower than the other 2 isotopes, so I'm guessing we're going to get something in between 220.9 and 220. It's not going to be down there. So I could probably eliminate 218.5. I could eliminate B, because these 2 only constitute together 25.78% abundance of those 2. This is still most of it. 221, well, neither of these is over 220, so that wouldn't be a candidate. Well, by process of elimination, that's going to be our answer, but let's go ahead and figure out how to compute it. So the average atomic mass is going to equal, we'll start with isotope 221's actual mass, which is 220.9, 220.9 AMU. We're going to multiply times the percent abundance. Now, in the percent abundance, I want percent just means per 100, so I'm going to take that 74.22 divided by 100. Now, some of you may have already figured out that, well, all I'm doing is moving the decimal place over 2 places to the left, because I want to get this out of percent and into a decimal. And then we're going to come down to isotope 220. And its actual mass is 220. So that's 220.0 AMU times its percent abundance, which is 12.78. And we're going to divide that by 100 to get it into percent. Into a decimal. Then we're just going to add the last one. And the last one is isotope 218, which has an actual mass of 218.1, and then we're going to multiply that times its percent abundance, which is 13.00. We'll divide that by 100. Now, when you plug this into your calculator, I wouldn't bother computing these as individuals. I would simply plug in 220.9 times 0.7422, or you could do 74.22 divided by 100 plus 220 times 12.78 divided by 100. I'm just in my head going to go ahead and move the decimal place over, plus 218.1 times 0.13, and in fact we do get 220.4 AMU. And that is our weighted average, our average atomic mass for isotope X in this particular problem. You might keep in mind that, let's say they didn't give you the percent over here for the isotope 218. You could have derived that simply by adding 12.78 plus 74.22, subtracting it from 100. That would have given you 13. You may be called upon to calculate the mass of one of the isotopes given the average atomic mass. Now, they may not give you the average atomic mass, but remember, if it's a real element, you can always get the actual weighted average of that element from the periodic table. Okay? All right, I think that's enough for this particular video.